Hello, welcome back. In the discussion of the oxidative cyclization reactions, we have seen oxidative cyclization processes in three different categories mainly, but today we will mainly focus on the application of this oxidative cyclization technique mainly for the natural product synthesis. Before that, let us look at this oxidative cyclization method and what other transformation we can utilize or we can incorporate into this oxidative cyclization method. After discussing that, we will get into the discussion of few natural product fragment synthesis by utilizing these very useful techniques. So, oxidative cyclization reactive intermediate we can first discuss. Reactive metal fragment. Well, first most important thing is to deliver the cyclopentadienyl zinc or zirconium intermediate by utilizing this technique. So, cyclopentadienyl zirconium species are available with, let us say for example, you can prepare very easily zirconium chloride, but from there on what we are essentially looking at the cyclopentadienyl zirconium species. For this purpose, as you can see that two chlorides are there, we can take two equivalent of N-butyl lithium. This is reported by Nigisi in 1987. Two equivalent of N-butyl lithium can be reacted to give you the Cp2 zirconium and dialkyl intermediate, right. From there on you can have these these processes where this hydride is basically undergoing beta abstraction. This is alpha beta, zirconium in zirconium 4th plus. So, therefore, there is no possibility of undergoing a beta hydride elimination from this process. From here on, a beta abstraction at this position will gives rise to the intermediate formation that will see Cp2 zirconium and then cyclopropane intermediate utilizing zirconium and your ethyl part over there. Overall, from this part you will get the C4H9 formation, which is the alkane formation from there. So, this is the beta abstraction intermediate that gives rise to this zirconium Cp2 and the cyclopropane intermediate. What we have just now then seen how to prepare free or so called free cyclopentadienyl zirconium intermediate, because that zirconium cyclopropene intermediate we can get rid of this cyclopropene intermediate in the form of olefin, right. Before that, what we started with is dicyclopentadienyl zirconium chloride, which then can be reacted with N-butylene to give you of course, two equivalents of lithium chloride and two alkyl unit on the zirconium. From there on, since zirconium is in +4 oxidation state through at the first two steps, then what we have seen is it cannot undergo the beta hydride elimination, because for beta hydride elimination you need to have the electron available to participate into the process. Therefore, one alkyl group will take up the beta position hydride directly to give the alkane, and during the process we will get a metallocyclopropane ring formation. By doing so, we will have an intermediate which is ready to leave the metallocyclopropene to an olefin intermediate to give you the Cp2 zirconium, which is the active species, which is what we need for our substrate such as alkyne and olefin to put together. So, the reaction whatever we have seen just right now are of not much importance, except the fact that it can cleanly provide the formation of dicyclopentadienyl zirconium species, which is the real active species that will be required for the next step of the process. That is our the main goal, or that is the main thing we were looking for. So, all this reaction what we have discussed is nothing but for the formation of Cp2 zirconium, where this olefin can go out. Let us look at the enine cyclization, where we will be discussing one in substrate, another ine, that means alkyne substrate, one olefin, one alkyne put together, we will try to build a complicated molecule by, or the value added molecule, by utilizing this Sp2 zirconium species. We have just right now seen how to generate this cyclopentadienyl zirconium species. Now, utilizing those cyclopentadienyl zirconium species, we would like to get the enine chemistry. Let us get into the enine chemistry. Enine cyclization. What we have essentially is, quote unquote, you can put it in quote, this is not really the directly form intermediate, you have to synthesize in situ, and along with it, if you have olefin with it, we do have in and ine as an intermediate. From here on, what we do see that cyclopentadienyl metal and this olefin and alkyne is reacting with it. First the alkyne will be reactive, and therefore we get the intermediate where olefin is appended from the metal center. So, olefin is kind of coordinated with the metal center, you can draw that bond. So, interaction between the metal and olefin. So, first alkyne interacting with this dicyclopentadienyl zirconium species to form this cyclopropene intermediate. From there on, the olefin can coordinate with the metal center to gives rise to an intermediate or a process where the insertion of the olefin can then take place to this cyclopropene intermediate. Overall, then we will have dicyclopentadienyl metal and this organometallic intermediate, where it is nothing but a metallocyclopentene intermediate with another 5-membered ring associated with it, right. From there on, if one wants, one can look for. So, let us say for example, we are putting R, so we should follow the R, and then we can put for example carbon monoxide to it to give rise to the overall the process where we have this cyclopentane ring. Along with this, we have a keto and the intermediate that can be cyclized further. So, the carbon monoxide can be inserted at this position to give rise to this beautiful molecule. If you are reacting with iodine, for example, this metal carbon bond can be iodinated very beautifully to overall gives rise to the species where a exocyclic double bond and R and diiodo can be synthesized from these processes. Okay. So, what we have seen right now is a very powerful technique where both alkyne and olefin are together in one substrate. Dicyclopentadienyl zirconium participate into the reaction by interacting with alkyne first, in the way it forms the cyclopropene intermediate. That cyclopropene intermediate then interacts with the olefin, the remaining olefin, which was less reactive compared to the alkyne. Now, that interaction leads to the incorporation of the olefin into the cyclopropene ring to form the 5-membered metallocycle intermediate. That 5-membered metallocycle intermediate then can be reacted with other for example, other electrophiles such as iodine can be reacted, because this is a organometallic intermediate already in there. In fact, 2 of them, both of those metal carbon bond can be, for example, iodinated, or we have seen carbon monoxide can be incorporated into this metal carbon bond. Overall, we can then have a 2 cyclopentane ring, 5-membered ring, or a 5-membered and a 6-membered ring together for these oxidative cyclization processes. Let us look at it, the few more characteristic of these oxidative cyclization process. So, using these dicyclopentyl zirconium species, which is nothing but your Cp2 zirconium chloride and 2 equivalent of N-Bewley, that is what you need. cyclopentadienyl zirconium species is in situ generated by cyclopentadienyl zirconium chloride and 2 equivalent of N-butyl lithium. Overall, this is the reactive species. This is a experimentally very simple procedure and works to provide 5,5 or 6,5 enone system. Also, terminal alkynes not tolerated under this reaction condition, and substitution on olefin however is also limited functional group compatibility also is shown, and terminal alkynes are not tolerated during these processes. So, overall we now know that there exists some limitation of the processes. If we have the substitution at these different olefin and alkyne, some of those substitution will not be tolerated. However, still this is a very important method despite some limitation, as we said, these are important method for synthesizing natural products. We will come in a moment. Let us first point out the limitation of these methods. So, limitation of these methods are very simply, functional group compatibility is not that very high. We have terminal alkyne does not work, terminal alkyne does not work for this process. We have to always then deal with the internal alkyne, and in substitution on olefin substitution is limited. That is also another problem, but the good things are it is experimentally simple procedure and works to provide 5,5 or 6,5 different these enone systems. So, there are good things, but there are limitation of the method as well for these processes. Let us look at then few of these natural product synthesis where this enine method or enine technology can be utilized for a value added compound synthesis. So, for the rest of the class we will discuss how different natural product can be synthesized or is reported by utilizing this technique. Okay. So, first we will discuss the natural product synthesis by Wender. Back in 1990 they have reported it. What they have reported simply is an advanced intermediate where all these in and ine are beautifully placed to give rise to an intermediate where CO2 T-butyl and this alkyne is appended with it. Of course, as we said, we cannot have a terminal alkyne. So, internal alkyne is fine, TMS protected, which is nothing but a bare alkyne if you would like to have it. If your process is not tolerant of terminal alkyne, that is what you put a TMS, which can be deprotected later on. And so, what we have here is an in and ine. So, in ine chemistry we are looking at this cyclopentadienyl zirconium species. As you know, cyclopentadienyl zirconium dichloride and N-butyl lithiums can be used to form this. Overall, then we will have an intermediate where this whole compound can be drawn correctly, can be formed correctly as well to give rise to this intermediate where you have this cyclopentadiene or zirconium 5-membered intermediate, right. So, overall we are seeing the bond formation between this and zirconium is getting incorporated in here, right. So, therefore, what we have seen that zirconium Cp2 intermediate is formed. From there on, if you are reacted with CO, you should be able to incorporate the CO over there to form you the advanced intermediate that is required for the Duffnain synthesis. So, let me draw this intermediate where you will have both a 6-member and a 5-member as well as this larger heterocycle where we have different substituent at this position that is tolerated for this value added product synthesis, which is then converted to corresponding Daphne synthesis. Okay. So, the natural product Daphnenes can be synthesized, Daphnenes Tiglens can be synthesized, Tiglens can be synthesized by utilizing this technique. So, this is a very powerful technique. What you have also seen here is the functional group, although this process is not that great for tolerating different functional group, we have seen ester is tolerated in the process. We have olefin and alkyne put together in these processes to form a 5-membered ring, which is coupled with another large member heterocycle 1, 2, 3, 4, 5, 6, 7-membered heterocycle overall. So, 5-membered, 7-membered and 6-membered heterocycles are overall put together by utilizing this technique. This is going to be a useful technique for synthesizing a number of natural product. We will see few of them right away. Okay. Some more natural product synthesis by utilizing this anion chemistry, which has already been reported, and these are turned out to be quite an efficient method for preparing these fused multicyclic intermediate which is required for a number of natural product synthesis. Let us look at the another Wender synthesis. Wender, this is Jacques 1997. This is once again very advanced intermediate we will draw from here on. This is a 7-member intermediate 1, 2, 3, 4, 5, 6, 7. Okay. So, 7-member intermediate we would like to draw here, and in the process what is essential is to have an anion into the business, right. Into the substrate we have in and we have the ion. Once again this is an internal alkyne, and we have the alcohol, a tertiary alcohol protected by TMS, and you also have OTBDMS protection over there for this another alcohol that is out there for the natural product synthesis. Now, we have a 6-member intermediate as well, where O acetate and methyl is there, and then we have a hydrogen up there. From this intermediate, if you have the cyclopentadienyl zirconium, what once again you can put together is this olefin and the alkyne can be incorporated, can be stitched together. So, let us not draw the remaining part. So, simply we can have zirconium Cp2 intermediate that is incorporated into the substrate to gives rise to, we are not drawing the rest of the intermediate. So, rest of the intermediate can be, so this from this part and this part that can go on, and finally, if we are taking acetic acid HOAC acetic acid into the picture, what we overall get is the formation of a methyl and a terminal or internal olefin in this case to gives the advanced intermediate for a natural product synthesis as well. Well, this is very powerful technique. As you can see that chemistry is very simple. You have an ion, that is one in and one ion, one olefin and one alkyne. You can put them together with cyclopentadienyl zirconium intermediate, and finally, depending on the target molecule, you can incorporate either proton or iodo or even carbon monoxide or even other electrophile during the processes for synthesizing the natural product or any complex molecule of interest. We will see few more example of the similar type, where again once again in and ion are put together to give rise to the desired product formation. Let us look at one more compound, where indeed now we will see that olefin and olefin coupling is happening rather than in and ion, that is also possible. Let us look at one such example. This is by Mori in JOC 1992. The substrate that we have in hand is the one where we have a terminal alkyne and two terminal alkyne, one is less substituted, another is more substituted, and another internal alkyne as you see in here. We have this substrate, we have terminal olefin and internal olefin, but this is disubstituted, this is monosubstituted. Obviously, this is the one which is more reactive, and it would be reacting with dicyclopentadiene zirconium intermediate as one would expect. Subsequently, we will get the cyclized intermediate. From there on, we can have this zirconium Cp2 cyclized cyclopropane type of intermediate. Other things are remaining intact without any problem, and from there on what we do get is the attack of or participation of this olefin with this cyclopropene ring overall to give a very interesting intermediate that would lead to dendrobium synthesis. Let us look at this natural product synthesis where a fused 6-membered ring with the 5-membered ring now with NBN, and of course, then we can have a methyl group on top. Overall, we do have the hydrogen on top in this case, and in the process we have zirconium incorporated and Cp2 ring also in there. So, 2 cyclopentadiene ring with zirconium, this is a 5-membered ring, another 5-membered ring and a 6-membered ring appended with a disubstituted olefin is produced. Overall, over here in place of zirconium we can introduce the carbon monoxide in there to synthesize the dendrobium, which is a very interesting natural product, but can be put together very easily by utilizing this cyclization technique by which is reported by Mori in 1992. Overall, the final compound will look like from this oxidative cyclization reaction, we can get then N-benzyl intermediate along with the all the decoration that is required for this product formation. We have keto, that is coming from here. We have Cp2 zirconium intermediate that will give rise to this product formation very efficiently by utilizing this oxidative cyclization technique. Well, that is once again is a very powerful technique. As you have seen, here we have instead of an in and ine, we have 2 in. One is terminal olefin monosubstituted, another is internal one. Of course, that is the one which is very close to the terminal one that can participate into the cyclization reaction. The other one, other olefin that we are having, the disubstituted one, although this is terminal, but it is not. It is placed in a far away place which cannot be really participating that easily for the cyclization reaction. Overall, then we have an intermediate where quickly fused 6-5-5 ring formation is possible to give rise to the one of the very beautiful natural product, simple and very beautiful natural product. Well, let us look at some more example of this type of oxidative cyclization reaction that is required for these various product formations processes. Well, we will now look at the pentalenic acid synthesis by utilizing this anion chemistry. This is a very powerful technique. Again, it is reported by Nigisi in JACS 1991. What we see here is, now once again back to the anion chemistry, we have a protected alkyne and a protected alcohol, because otherwise it will not be tolerated. Overall, what we see an anion chemistry which will give rise to the simple intermediate with ROR alkyl alcohol protected and methyl dimethyl one, and the hydrogen should be over here. Overall, we have a double bond and CO generated from this process. So, of course, we are using the Cp2. So, we are using Cp2 zirconium intermediate from Cp2 zirconium dichloride and along with N-butyl lithium. Along with this, we are utilizing carbon monoxide to give rise to this intermediate, which can then further converted to pentalenic acid by using the further transformations. So, once again we have seen various natural product synthesis by utilizing this technique, which is very interesting, and what in the next class we will be then discussing is the beta abstraction, how the beta abstraction will give rise to this alkyne intermediate from which we can do once again this beautiful chemistry, that anion type of chemistry that one will be interested in doing. There remains a number of limitations of this anion chemistry as we were discussing for this type of reactive intermediate formation. This is where beta abstraction by this other method to prepare cyclopentadiene zirconium can be very useful, that we will be seeing in the next class. In today's class, we have seen then anion chemistry, where both the double bond and alkyne is participating into the reaction beautifully. In fact, in one case we have seen 2 olefin are even participating together, but in all these cases we can synthesize a number of natural products which are very complicated looking fused rings. It could be 676 or 655 or different variety of other variation of these fused rings that can be synthesized by utilizing the cyclopentadienyl zirconium chemistry. For cyclopentadienyl zirconium synthesis, we have started with dicyclopentadienyl zirconium dichloride intermediate and reacted with the organolithium reagent N-butyl, which then gives rise to the dialkyl zirconium dicyclopentadiene species, from where a beta hydride elimination is unlikely, and therefore beta abstraction goes on to give you the alkane, that is butane, and the remaining part can give you the cyclopropane metal intermediate, which can then gives rise to the get rid of the olefin to give the cyclopentadiene zirconium product. Now, this cyclopentadiene zirconium is almost can be thought as a free cyclopentadienyl zirconium species, which is free to react with anion formation, or to give specifically reacting first with alkyne, which is more reactive towards this zirconium, and then those cyclopropene intermediate can usually react with olefin to give the desired product. In the next class, we will discuss more of this oxidative cyclization technique, and also we will be discussing 2+2 cyclotrimerization reaction along with the Poisson-Khond reaction, and till then please keep studying these methods, which are very powerful for synthesizing very complicated molecule, which is otherwise will not be possible by any other technique that very easily. All right, till then, bye bye.